Picture the scene, okay. We are down here on Earth, currently spending over $4 billion on this brand new, shiny space telescope.
Oh, yeah.
And it's being unveiled today, right? Just to try and map the completely invisible parts of the universe.
Right.
But then, simultaneously, right now, out in the pitch black of deep space, there are these agonizing, giant, dying stars that are literally swallowing their own planets whole.
It is a literal cosmic apocalypse happening out there as we speak.
Yes.
And here we are just, trying to build glasses big enough to get front row seats to the destruction.
Exactly. It is just a lot of drama for a Wednesday, I think. So, hello and welcome to another deep dive.
Welcome, everyone.
Pull up a chair, grab your coffee, because on Casutalks today, and today is Wednesday, April 22nd, 2026, our mission is just an absolute mind bender.
It really is.
We are digging into a huge stack of sources. We've got fresh astronomical data from NASA, a wild new study from the monthly notices of the Royal Astronomical Society.
Well, that one is intense.
Super intense, plus some cutting-edge pharmacology research out of Brookhaven, and this massive, massive health data review from molecular psychiatry.
Yeah, that one is going to surprise people.
For sure. So we are taking all of this and investigating how science is finally spotting the invisible and the overlooked.
Right.
And we're going to do this by traveling from the most violent cosmic scales in deep space all the way down to, microscopic fragments of medicine inside our own bodies.
And what makes me so incredibly excited about today's stack of research is the sheer dizzying change in scale.
Yeah.
Because if you think about it, and I really want you listening right now to ponder this, it does not matter if we are talking about a giant gas planet orbiting a dying star or a tiny 100 Dalton molecule clicking into an enzyme in your bloodstream.
Okay.
When you really get down to the mechanics of it, everything is dictated by incredibly delicate, completely invisible physical connections.
Oh, I love that. Unseen forces, right?
Exactly.
Okay, let's unpack this macro side first, because we actually have an event happening right over our heads.
Oh, yes, we do.
If you have the chance to look up at the sky tonight, you have to do it. Today, April 22nd, is the absolute peak of the Lyrid meteor shower.
Beautiful.
And I love a good astronomical trivia moment. These meteors are actually ancient pieces of debris from Comet Thatcher, which is wild because Comet Thatcher takes 415 and a half years just to make one single orbit around the sun.
That is just staggering.
Right, so the stuff we are seeing burn up tonight was left behind centuries ago.
It really is this beautiful, accessible spectacle. All you need is a dark patch of sky and a little patience. You definitely don't need a $4 billion telescope for this one.
Definitely not. The expectation for tonight is about 15 to 20 meteors per hour.
Okay.
And they are tearing through our atmosphere at an astonishing 30 miles per second. Yeah, and if you trace their path back, they appear to originate from the constellation of Lyrid right near that super bright star Vega. Oh, and there is a fun bonus for tonight, too.
What's the bonus?
The Moon and Jupiter are going to be pairing up beautifully in the sky, right near the Gemini twins.
That is going to be a gorgeous alignment. I hope the weather holds up.
Me too. But, so here is where it gets really interesting and honestly a little funny to me.
Okay.
I was reading up on the mechanics of the Lyrids. And unlike the Leonids, which the Earth basically just plows into head-on during our orbits.
Like hitting a wall of bugs on the highway.
Exactly. But the Lyrids, they catch us from the side. So if Earth was a car cruising down the orbital highway, hitting the Lyrids is basically like getting swiped on the left front fender.
Oh, wow.
I just love the visual of a cosmic fender bender.
That is the perfect analogy. It's just a light scratch on the planetary paint job.
Yep.
But, while our night sky feels so peaceful and poetic with these little shooting stars bouncing off our fender,
Right.
in other parts of the universe, the physics are playing out with terrifying violence. Remember you mentioned dying stars swallowing planets a minute ago?
Oh, I did. And you have to explain this to me, because swallowing a planet sounds like something straight out of a sci-fi horror movie.
It really does.
How does a star actually do that? Does it just, puff out until the planet is suddenly inside it?
Well, the puffing out is part of it, definitely, but the actual mechanism is incredibly violent.
Okay.
So this comes from a new study using data from NASA's TESS satellite. That's a transiting exoplanet survey satellite.
Right.
The researchers looked at 500,000 stars, and they zeroed in on red giants.
Remind me, what makes it a red giant?
These are older, aging stars that have exhausted the hydrogen fuel in their cores. So when that happens, the core contracts, but the outer layers expand massively.
Okay, so it swells up.
Yes. And what the data revealed is that these expanding red giants are actively devouring the giant planets that orbit close to them.
But what is the actual mechanism? I mean, why doesn't the planet just keep orbiting inside the puffed out gas?
This is the dramatic part. It all comes down to a gravitational tug of war. Astrophysicists call it tidal interaction. Let's bring it back home for a second to explain the how. You know how our moon exerts a gravitational pull on the Earth, right?
Right, yeah.
That pull actually creates a physical bulge in our oceans, which we experience as the tides.
Right. The water gets literally pulled toward the moon.
Exactly. Now scale that up. A massive gas giant planet orbiting very close to a star exerts a gravitational pull on that star.
Wait, the planet pulls the star?
Yes.
Yeah.
It creates a tiny bulge on the star's surface. But as the star ages and swells up into a red giant, its outer layers get closer to the planet.
Oh, I see.
And this tidal interaction becomes incredibly intense. Because the star is rotating, that bulge of stellar material is constantly interacting with the planet's gravity. It acts like a massive cosmic brake pad.
A brake pad.
Yeah. The planet is pulling on the star's bulge is pulling back, and this constant friction drains orbital energy right out of the planet.
Wow. So it's not just that the star gets bigger, it's that the gravity is actively dragging the planet down.
Precisely. It slows the planet down. And orbital mechanics dictate that if you lose speed, your orbit shrinks.
Oh, no.
So the planet gets dragged closer, which makes the tidal friction even stronger, which slows it down even more.
It's a death spiral.
It enters a total death spiral. Eventually, the planet is either ripped apart by the gravitational shear forces, or it plunges directly into the star's fiery envelope and is completely incinerated.
That is absolutely brutal.
It really is. And the test data proves it beautifully. Or, well, tragically, depending on how you look at it.
Right.
The researchers found that around younger stars, you see these close-in giant planets about 0.35% of the time.
Okay.
But when you look at older red giants, that frequency drops to just 0.11%. The planets are literally missing. They've been eaten.
Okay, I have to ask the question that I guarantee every single person listening to us right now is wondering.
Let me guess.
What does this mean for our solar system? Because our sun is going to turn into a red giant one day, isn't it? Are we the cosmic appetizer?
That is the ultimate question. But you can relax. You don't need to cancel your weekend plans. Our sun will eventually exhaust its hydrogen, yes, but not for about 5 billion years.
Okay, I think I'll be busy that week anyway.
Probably. Now, when it does swell into a red giant, the Earth's physical rock might actually survive.
Really?
Yeah, our orbit is far enough out that we might avoid the tidal death spiral that these close-in gas giants experience. We might just ride out the expansion.
Well, that is a relief.
I said the rock will survive. Life on Earth absolutely will not.
Oh, okay.
The sheer radiant heat from the expanding sun will boil away our oceans and melt the crust long before the star's surface even gets here.
Well, thank you for that incredibly grim clarification. At least we have 5 billion years to pack our bags.
Plenty of time.
But seriously, it just blows my mind that we can even know this. I mean, how do we measure a missing planet around a star that is thousands of light years away?
We build bigger, better eyes. That is really the only way.
Which brings us perfectly to our next source. Today is a massive day for astronomy because NASA officially unveiled the Nancy Grace Roman Space Telescope at the Goddard Space Flight Center.
Such a huge milestone.
This is a really big deal. They spent over $4 billion on this marvel. It features a 2.4 meter primary mirror, which is basically the exact same size as the legendary Hubble Space Telescope.
Right.
But here's the kicker. Roman has a field of view 100 times larger than Hubble.
It is a phenomenal piece of engineering.
Right.
To put that into perspective, if Hubble is looking at the universe through a tiny soda straw,
Okay.
the Roman Space Telescope is looking through a massive panoramic bay window.
Wow.
And because of that wide view, the data it is going to collect is just staggering. We are talking about beaming 11 terabytes of data back to Earth every single day.
Wait, let me wrap my head around that. 11 terabytes a day from space.
Every single day.
How is that even possible? My home internet struggles with a simple video call.
Well, NASA uses the Deep Space Network and these incredibly high-frequency Ka-band radio transmitters to downlink that much information.
That's wild.
But the real challenge isn't just getting the data, it's what is actually inside it. Rome's primary mission is to map the 95% of the universe that we completely fail to see with traditional light.
You mean like dark matter?
Exactly, dark matter and dark energy. And it's going to hunt for new exoplanets, using a technique called gravitational lensing.
Okay, let's unpack gravitational lensing because I read through the briefing on this and the concept is so cool.
Go for it.
So, for you listening, imagine you are sitting at a cafe. You have a big curved wine glass full of water right in front of you.
Okay, I'm picturing it.
If you look through the thick glass at the bottom, the background of the cafe, the tables, the people, it all appears totally warped, stretched, and magnified, right?
That is a brilliant analogy.
Thanks. Gravitational lensing is basically that exact wine glass effect, but on a cosmic scale. Einstein told us that really massive objects, like an entire cluster of galaxies, literally bend the fabric of space and time.
Right, space-time is curved.
So if there is a tiny, incredibly distant galaxy sitting way, way behind that cluster, its light doesn't travel in a straight line to get to us.
Because the straight line isn't straight anymore.
Exactly. It travels along the curve of that bent space-time. The massive cluster acts just like the curved glass of the wine goblet, magnifying and distorting the light from the galaxy behind it.
That's it, exactly. And sometimes, if the alignment is absolutely perfect, the light from the distant object is bent into a complete glowing circle around the massive foreground object.
Oh, the rings.
Yes, we call those Einstein rings. They are beautiful, but more importantly, they let us see things that are way too far away to ever spot normally.
Because they're basically natural magnifying glasses.
Precisely. But here is the catch. When you are downloading 11 terabytes of wide field imagery every single day, finding these warped little rings is literally like finding a needle in a cosmic haystack.
So who is doing the looking? I mean, surely they aren't just putting interns in a room with a billion photos.
Well, they tried using machines first. If we look at the European Space Agency's Euclid telescope, which does similar wide field surveys,
Yeah.
they ran into this exact data deluge problem. They used machine learning and AI to sift through an initial batch of 72 million galaxies.
72 million, okay.
The AI was looking for the mathematical signatures of these warped shapes, and it did a really good job. It whittled those 72 million down to about 300,000 images that likely contain gravitational lenses.
But 300,000 is still a massive number to look through.
Exactly. And AI is not perfect. It gets confused by weirdly shaped galaxies or camera artifacts or overlapping stars.
Right, it sees a smudge and thinks it's a ring.
Right. It needs human eyes to confirm the results.
Yeah.
Because the human brain is uniquely evolved to spot patterns and anomalies in visual data in a way that code simply cannot replicate yet.
And this is where it gets really exciting for you listening, because you can actually help. Science needs you.
It really does.
Through a project called Space Warps on the Zooniverse platform, everyday citizens can log on, look at these 300,000 pre-selected images, and essentially play a game of cosmic spot the difference.
It's amazing.
You literally just click on the ones that look like they have a lens or an Einstein ring.
Yeah.
The scientists are expecting this crowdsourced effort to uncover over 10,000 new gravitational lenses.
10,000.
Yeah. And to put that in perspective, we only found about 500 in the last major data release. You could literally make a groundbreaking astronomical discovery while drinking your morning coffee.
I love how democratized science is becoming. And what a fascinating transition this gives us for our next topic.
Oh, yes.
Because we just spent all this time talking about using colossal gravitational lenses to magnify entire galaxies in deep space.
Right.
But researchers right here on Earth are doing the exact opposite. They are using microscopic lenses to solve life and death mysteries inside our own cells.
That is a perfect pivot. Let's dramatically shrink our scale here. So I was reading this fascinating research out of the Brookhaven National Laboratory.
Yeah.
They are using a technique called macromolecular X-ray crystallography, which, I mean, that is a mouthful.
It really is.
But it essentially acts like an incredibly powerful microscopic lens. And they are using it for something called FBDD, which stands for fragment-based drug design.
This is genuinely revolutionizing pharmacology right now.
Totally. The source material had this fantastic analogy for it. Think about traditional drug discovery, where they try to design these massive molecules, usually 500 daltons or larger in molecular weight.
Okay.
It is like trying to solve a 10,000-piece jigsaw puzzle, but you don't have the picture on the box, and you are trying to force huge clusters of pieces together, just hoping they fit the gap.
Sounds frustrating.
Very. FBDD, on the other hand, throws out the giant clumps entirely. It uses tiny, incredibly simple chemical fragments. We are talking just 100 to 300 daltons. But wait, let me push back on this for a second because I was confused.
Okay, what's the hang-up?
If these chemical fragments are so tiny, Aren't they missing a lot of the complex chemical hooks needed to actually grab onto a disease target?
That's a great question.
Wouldn't they bind to the disease proteins incredibly weakly compared to a massive drug molecule?
You are spot on, and that is exactly what happens. Initially, these tiny fragments bind very, very weakly to the target protein.
Okay, so why use them?
Because here is the genius of the method. They bind with incredible structural efficiency.
What does that mean, practically speaking?
Okay, imagine a disease-causing enzyme as a lock with a bunch of weird hidden tumblers.
Yeah.
A giant, bulky 500 Dalton drug molecule might be too clumsy to fit into the deep crevices of that lock.
Right, it's just too big to get in there.
Right. It might jam the lock, but it's not a perfect fit.
Ooh.
A tiny 100 Dalton fragment, however, is so small that it can slip right into the deepest, tightest nooks and crannies of that enzyme.
Whoa.
So, using that X-ray crystallography lens we mentioned, scientists shoot X-rays at the protein to see exactly how and where that tiny fragment attached itself.
To see if it fits a specific tumbler.
Exactly. Once they see that perfect tiny foundation, they start building.
Oh, I see. So they find the tiny piece that fits perfectly, and then they build the rest of the drug around it.
Yes. Because the fragment is so simple, they can use advanced robotics and artificial intelligence to add new chemical bonds to it, step by step.
Wow.
They optimize it. They basically grow the molecule in the lab, customizing it to fit the exact 3D shape of the disease protein. They turn a weak, tiny fragment into an incredibly potent, laser-targeted superdrug.
That is mind-blowing. It's like finding a single tiny tooth of a key that perfectly hits one tumbler and then just 3D printing the rest of the key while it's inside the lock.
That's a great way to picture it.
And they aren't just theorizing this, they're getting real results. The Brookhaven team just used this FBDD method to target an enzyme called BLVRB.
Okay.
And this is huge for oncology because targeting this enzyme could completely revolutionize how we treat a major side effect of chemotherapy.
Really? Which one?
So many cancer patients suffer from a severe reduction in blood platelets due to chemo, which, often forces them to actually halt their life-saving treatments.
That's terrible.
Yeah. If this new highly targeted drug works, it could protect those platelets.
It is brilliant science. And if we connect this to the bigger picture of today's deep dive, tinkering with these microscopic atomic level pathways really demonstrates a profound truth.
What's that?
Human biology is incredibly sensitive, especially during periods of rapid development, like pregnancy.
Definitely.
When you introduce small molecules into a complex biological system, the ripple effects can be massive, and sometimes they are entirely unforeseen.
Which brings us to the final and perhaps most sobering piece of research in our stack today.
Yeah, this one is heavy.
A massive new study was just published in the journal Molecular Psychiatry. And when I say massive, I mean it. They used the Epic Cosmos database to analyze the health records of 6 million children in the United States.
That sample size is just staggering. 6 million.
It really is. And they were looking at a very specific connection. They found a statistically significant link between pregnant mothers taking a class of medications called SBIMs.
That stands for sterile biosynthesis inhibiting medications.
Exactly. They found a link between those and an increased risk of their children being diagnosed with autism spectrum disorder, or ASD.
And this is where we really need to understand the why and the how at the molecular level, because it connects right back to how our bodies build things.
Right.
Often we hear the word cholesterol and we immediately think of clogged arteries and heart attacks. We view it as a villain.
Oh, 100%. Bad cholesterol, right.
Right. But fundamentally, biologically, cholesterol is absolutely crucial for life.
It's a building block.
More than just a block, it is the mortar in the brick wall of your cells. Cholesterol is required to build the lipid bilayer of cell membranes. It keeps those membranes fluid but stable.
Okay.
And in a developing fetus, the brain is building millions of new neural connections and cell membranes at an astonishing rate. It needs a massive supply of localized cholesterol to form properly.
And the medications interfere with that?
Yes. Medications like SBIMs, which include certain statins used for high cholesterol, or certain antipsychotics like cariprazine, they're designed to inhibit the biological pathway that produces sterols.
So if a pregnant mother takes these drugs, the fetal brain isn't getting the mortar it needs.
It's actually a twofold problem. First, the disruption of the pathway might deprive the developing brain of the cholesterol needed for neuronal differentiation and synapse formation.
That makes sense. What's the second part?
Secondly, when you block a metabolic pathway halfway through, you get a backlog. The study suggests these drugs cause a buildup of intermediary molecules called reactive oxystrols.
Oxystrols, okay.
Yeah, and these oxystrols can be toxic to developing brain cells and can trigger inflammation.
Wow. The statistics in the study really illustrate the impact of that disruption.
They do.
They found that the risk of a child receiving an ASD diagnosis jumps 1.33-fold with each additional SBIM medication prescribed to the mother.
Goodness.
And it scales up. If a mother was taking 4 or more of these specific sterile inhibiting medications during pregnancy, the risk of autism in the child more than doubled.
That is a very significant jump.
But, and I really want to pause here and play devil's advocate for a second.
Please do.
Because we have to be rigorous about how we interpret medical data. This study of 6 million kids was purely observational, right? They looked at past medical records.
That's right.
We cannot look at this data and definitively say these drugs cause the autism.
No, we can't.
Because couldn't it be that the mother's underlying conditions, say a severe psychiatric disorder requiring the antipsychotic, or a severe metabolic syndrome requiring the statin, might be the actual genetic or environmental trigger for the autism rather than the chemical itself?
You hit the absolute nail on the head. That is the critical nuance, and the researchers themselves entirely agree with you.
Oh, they do?
Oh, absolutely. We cannot definitively claim direct causality from an observational database study. There are always confounding variables. The vital takeaway for you listening is this: nobody should read this headline, panic, and suddenly stop taking medications that are essential for their physical or mental health.
Absolutely not. Do not alter your medications without a doctor.
Exactly. What this study actually represents is a loud, vital call to action for the medical community. It is a signal for doctors to carefully reevaluate their prescribing habits.
Especially with multiple medications.
Yes, specifically when it comes to prescribing multiple SBIMs simultaneously during pregnancy.
Yeah.
It is about taking a pause, looking at the complex molecular pathways we are altering, and carefully weighing the vital clinical benefits for the mother against these newly identified potential risks for fetal brain development.
So it's about personalized risk assessment.
It is about informed, personalized medicine.
It is the ultimate tightrope walk of medical science. Everything is just so deeply interconnected.
It really is.
Wow. I have to say, what a journey we have been on today.
We really went everywhere.
We did. We started by watching expanding red giant stars swallow gas planets whole through tidal gravity. Then we looked through $4 billion space telescopes to map the invisible dark matter of the universe.
And then we zoomed way in.
All the way into the microscopic, looking at how 100 Dalton chemical fragments can save cancer patients, and how disrupting a single fetal cholesterol pathway can alter the development of a human brain.
It's breathtaking. And if I can leave you with one final thought to mull over today, it is this.
I'm ready.
Whether it is the immense gravitational pull of a dying red giant dragging a planet to its doom, or the microscopic chemical bond of a tiny drug fragment finding its perfect lock in an enzyme, our universe, at every single scale, is entirely dictated by unseen forces connecting things together.
Wow.
So as you go about your day, ask yourself, what invisible forces, what unnoticed habits or silent connections in your own life are shaping your trajectory right now without you even realizing it?
Oh, I love that. A little existential homework to go with your coffee.
It's a little bit.
That is absolutely brilliant. And on that deep, provocative note, we are going to wrap up today's deep dive.
Thanks for listening.
Thank you so much for joining us on this wild ride across the scales of the universe. Please join us again tomorrow as we brew another pot of coffee and explore more fascinating sources.
Can't wait.
Be sure to like, share, and subscribe to the show. And hey, if you made it all the way to the end, drop into the comments and leave us a funny phrase so we know you were here.
Oh, I have a suggestion.
Based on today's chat, I suggest commenting Space Jigsaw or maybe Cosmic Fender Bender.
Cosmic Fender Bender is perfect.
Have a wonderful day, everyone.
Take care, everyone. Keep looking up and keep looking close.